Good morning to everyone. My name is Kwa, and today I am going to talk about the borrowing hydrogen methodology, which is a very interesting concept in synthetic chemistry. But before we go so far, let's refresh your basic knowledge with organic chemistry year 2 by asking a simple question. How do we synthesize the amine? One of the strategies that we can think about is the reaction of primary amines with the alkyl halide. For example, let's talk about the reaction between ammonia and butyl iodide. We may expect that this amine will be the main product of this reaction. But you know, life is not easy. Actually, this reaction will form a complicated mixture at which the secondary amine, tertiary amine, and even the ammonium salts will be formed. If we control the equivalence of ammonia very carefully, the unexpected mixture is still formed. Additionally, many alkyl halides are toxic, so this strategy is not much useful in the amine synthesis. So how about synthesizing the amines from the alcohol? Alcohol is the functional group in many organic compounds, and many alcohols are commercially available. In this case, we can think about oxidizing the alcohol to form the aldehyde or ketone, then let the carbonyl undergo the condensation reaction with the amine to form the imine. Finally, the imine can be reduced by reducing reagents such as sodium cyanoborohydride to form the amine. This strategy is much more useful than the alkylation reaction. However, it is quite long, and we need to work up, purify the products after each step, which may require the chemist to take a longer time in the laboratory. Moreover, many oxidizing and reducing reagents are also toxic. So at this moment, you may ask yourself a question. Do we have any strategy to convert directly the alcohol into the amine in only one step? Can we use the nucleophilic substitution reaction to perform the synthesis? It is extremely challenging because the hydroxyl group is not a good leaving group for this reaction. Fortunately, chemists always knows how to overcome the obstacle. Borrowing hydrogen methodology, which I have mentioned in the very beginning of the presentation, will be the solution for this challenge. So, what is borrowing hydrogen methodology? Let's take a look in the diagram. The main idea of this concept is the use of the metal catalyst to store the activated hydrogen by borrowing the hydrogen from a donor molecule, which is the alcohol in this case. After several transformations, the metal hydride will return the hydrogen salts back to the molecules and form the desired product. So, in the borrowing hydrogen methodology for amine synthesis, the reaction will start with the dehydrogenation of alcohol, catalyzed by the organometallic compounds to form the carbonyl compound. Subsequently, the metal will be transferred into the metal hydride as you can see in the diagram. After that, the carbonyl undergoes the condensation reaction with the amine to afford the imine intermediate. In the final step, the hydrogenation salts in the metal catalyst, which borrow from the alcohol, will be returned to the imine intermediate and the amine will be formed. And then, the metal catalyst will continue the catalytic cycle to convert the alcohol substrate into the desired amine. So based on the diagram, we can somehow understand the power of the borrowing hydrogen methodology. First of all, instead of performing the oxidation, condensation, and reduction in each individual reaction, and spend many time to work up after each step, we can transfer all of them into only one pot and only need to purify the amine one time. Secondly, the last process, which is the hydrogenation step, is thermodynamically favored, so it can shift all three equilibriums towards the formation of the final product. So the reaction can proceed to form the amines with the relatively high U. Finally, it only generates water as a byproduct in the condensation step. So the borrowing hydrogen methodology can solve the environmental problems of synthetic chemistry, at which many traditional organic reactions produce a huge amount of unnecessary waste. As a result, this strategy can be seen as a particular example of green chemistry and the excellent process in the view of synthetic, economic, and environmental aspects. So far, we have discussed many aspects of borrowing hydrogen methodology and understand its advantage. At this moment, we will see the applications of this strategy in synthesizing the pharmaceutical drugs. For example, piribedu, which is an anti-Parkinson drug, can be synthesized from the piperazine derivatives and the piperonil alcohol, which are both commercially available. By using the borrowing hydrogen methodology, the target product can be synthesized in only one step with 87% isolated U. Additionally, chlorphenamide can also be produced in one step by the reaction of this alcohol and dimethylamine with the ruthenium compounds as the borrowing hydrogen catalysis. The target product was obtained with 81% isolated U. We can see that this process is extremely high atomic economy efficient, at which the final product can be synthesized with high U and water is afforded as the only byproduct. The catalyst is used with only tiny amounts and can be recycled for the next step. So far, we are coming to the end. To sum up, I would like to highlight again some of the key ideas of my presentation. Borrowing hydrogen methodology is an effective strategy to transform the alcohol into the amine compounds in one pot, with water as the only byproduct, and this concept has been applied to produce pharmaceutical drugs such as piribedu and chlorphenamide, as we have seen in the previous slides. From my point of view, this strategy will be receive more attention to synthesize useful organic products in the future. And this is the end of my presentation. Thanks a lot for listening.